Hello, Professor. My name is Leonardo Montes Yoca. I'm going to first start off by showing you my signature, printed name, red ID, and then go off into some concept to be able to solve the problem. So here's my signature, my name, and print. Red ID. Okay, so now I'm going to start out. Now I'm going to read the problem so we can have some sort of target. So what's happening is we have potential flow against a flat plate, which can be described with the stream function psi equals axy, where a is constant. This type of flow is commonly called a stagnation point flow, since it can be used to describe the flow in the vicinity of the stagnation point O. By adding a source at strength m at O, the stagnation point flow, a bump is obtained. So then what they want us to do is to determine the relationship between the bump height h, the constant a, and the source strength m. So what I'm gonna do is draw the diagram initially of what's happening in the flow, with the flow. So we have flow coming down to a target point O. Okay, so then they want us to see what happens after we add a source, which gives us an elevated height of 8. A source giving us the height of h here, with the flows here. Let's see here. We have our point again. There, this should be the climax here should be at the line. So yeah, they want us to analyze the m, a, and h variables. Okay, so the first thing we want to do is analyze what a source is. So a source is flow being projected radially outwards. So you can think of it such as like a firecracker, or more effectively a sprinkler. That's how I think of it. I think of it like a sprinkler. So then we have, I'm gonna draw this source here. And what we have is this diagram here on the right to explain our radial velocity, our tangential velocity, and our angle at which this is occurring. So UR is denoted by the streamlines, and our theta essentially gives us which one we want to select. And this is going to deem really useful in the problem because we find that we want to analyze it at pi over 2 at this one. Moreover to this, I'm also on to draw a cross segment, which is very thin on this. Draw a cross segment, want to draw a circle. And within this circle, a cross segment, so that we can get our formulation. So we know that the A is 2 pi r, the circumference the circumference of A is 2 pi r. So then we can use this UR formula to get our flow rate, which is based off the problem, and divide it by this specific A. In which case we want to verify by plugging in 2 pi r UR over 2 pi r. So we verify UR is equal to UR, we're good. So then what we want to do next is analyze U theta. We know that since our flow is going radially outwards, due to this, we have no tangential velocity, so we can say that our U theta is 0. All right, so what we want to do is, now that we have these two, we want to equate them to the Cauchy-Riemann. And by equating them, we can get to potential and our stream functions, which in case we'll now begin. Psi over theta. So this is for the radial velocity, and this is for tangential velocity. So then what we want to do now is solve for our cylindrical polar. Because when you have a source, when you have uniform flow onto a source, we tend to get these coordinates, or we tend to refer to it as cylindrical polar. 2 pi r is equal to this value. So then what we do, once we have this equation, we can integrate to get the value of the potential function. So we pull out the m over 2 pi, 1 over r dr gives us m over 2 pi ln r. right? So then that's the value of this variable here, m over 2 pi ln of r. So then what we denote that is this here can be represented as x. So we get which is our constant. All right. So now we do exactly the same thing for this other function denoted, which is this function here. And we equate it to the Cauchy-Riemann. I'm sorry, we equated it into the Cauchy in the top, but then we have to equate it one more time here, in which we get our value of psi to be m over 2 pi r. So we're doing essentially what we did at the top, but with this other function. R d theta equals m over 2 pi d theta equals m over 2 pi theta, right? So then I want to box this equation here because that's important, and also this one. Okay, so then these two equations are our stream functions. Okay, I know this is all a mess, so I'm gonna kind of we can just break off all this work, and I'm just gonna denote the two equations. UR is equal to 1r psi over theta, and psi is equal to m over 2 pi theta. All right, so then this is important because we want to make sense of these equations. So what we can do is we can go back to our source, in which case I draw here real quick. So we go back to our source and we look at our psi values for the streamline. So we can denote the psi 1, psi 2, psi 3. And the psi changes based on the specific angle. We also want to do, draw these little arrows here because they're going to show that we have equal potential because there are right angles from the specific streamlines. So this gets us to our equipotential, which in case we can go back to this equation, we can go back to the equation that we previously wrote as m over 2 pi ln of r, which in case we can plug in 0 for our r, in which we know that when plugging in ln of 0 returns an error on our calculator. And this is highly significant because it shows that at this point we have incompressible perfect fluid. It's showing the singularity at this point, which is sort of like a max peak value. So yeah, I'm getting a little off topic, so I'm going to relate back to the problem. So we have uniform flow and our source. So we have flow coming in to our source. And what this diagram looks like is, what we want to do is superimpose both of these to get a diagram to look like this. This is the fluid, and here we have the stagnation point, which is highly important because in the original problem, as the fluid's flowing onto the source, we are also having a stagnation point at pi over 2 when we analyze it at that point. So yeah, I'm just going to finish drawing this. We have this flow here also. So all this is the total flow. Okay. So then this total flow is represented by y is psi source plus psi uniform is our total psi. In which case we have psi is equal to m 2 pi theta plus ur sine theta. And then for this symbol here we have m 2 pi ln of r plus ur cosine theta. So then we can break it apart, and we know that our VR is 1 over r psi theta. I wrote this down, but when we look at this here, now we're analyzing it with the uniform flow, we can break it off into m 2 pi r plus u cosine theta. And for the v theta in this case, for this particular scenario, we'll have v theta equal psi over r, which is negative u sine theta. So those equations all these equations are very useful because it's built off what we're building off sort of a foundation, so we can solve the problem, in which I will now do so. So previously I drew the diagrams, so I'll just leave those out and just get to solving. So we get AXY plus m over 2 pi theta. Okay, so then we have, this is because of what, this comes from the earlier equation, and we can do we can equate our x value to our cosine of theta, as well as our sine of theta for the y value. Okay, so this is from our earlier equation. We just added it to what was given to us in the problem. So then we have AR cosine of theta times R sine of theta plus M theta over 2 pi, right? So then after that, we get this value here. Just simplifying my math. So this is our value for psi, okay? So then for now, what we want to do is, we know that at x equals 0 and r equals h, we know that at this point our VR is going to be 1 over r, as we previously explained from here, from this earlier equation. Sorry, that was from a different take, from a different video, but yeah, it's basically from the equation that we got earlier. This is a radial. Okay, so then now we have to do 1 over r. It's a over 2 r squared sine 2 theta plus m theta over 2 pi. So essentially what you're doing is you're getting psi, breaking in psi and putting it into this VR equation, and we're solving for VR, in which case we get 1 over r, a over 2 r squared cosine 2 cosine 2 theta, because that's how the math works out, 2 pi, okay, and then we get 1 over r ar squared cosine 2 theta plus m over 2 pi, and there we go. Okay, so now what we want to do, we have our VR, but now we need our v theta. So then for v theta, we know from the previous example, when comparing the source, when superimposing the source and the fluid flow, we get this value. Okay, so then we get this equation, sorry. So then we get, okay, so then we just plug in, once again, our psi that we solved for, and we get a over 2 r squared sine 2 theta plus m theta over 2 pi, right? So then we simplify that down, get r sine 2 theta. And as I said mentioned earlier, we're looking into our stagnation point, which occurs at q pi over 2 and r equals h, in which case our VR is 0 and our v theta is also 0. So then based off of this would be our equation. And now we're going to solve what they want for in the question, which is they want to know our A, our constant A, short strength M, and H. So now we have all these equations that we can relate that to, okay? So then we'll start here. We'll do VR is equal to 0. Okay, so then we have AR cosine 2 theta plus M over 2 pi R equals 0. So it's like what we did earlier, but now in terms of cosine. It's what we did earlier in this problem in terms of cosine. So then we get, analyze it at theta, pi over 2, or is H. So we do negative AH M over 2 pi H equals 0. And that breaks down to AH equals M over 2 pi H. In which case we simplify, we get H squared, M over 2 pi A. Take the radical of that. H is equal to M over 2 pi A as the final answer. This is our final answer, and this is how we relate our source strength, our constant of A, and our bump height, in which we can solve for the height of that with this final equation. Yeah, I'd just like to recap. We have a source strength. We have a uniform flow hitting a source strength, in which we have in which it hits a stagnation point. We get a stagnation point. So it's hitting here, we get a stagnation point, and we can ignore all the values within, in which we're just analyzing what's the fluid flow on the outside, which is essentially what we're doing here in this problem, and solving for the H on the outside. Another particular example, if we have a cylinder, we can hit it here, we have velocity 0 here, and maximum here. So it's just a matter of tying down all the concepts and applying them into solving this question, in which case I applied all the theory and plugged it into specific equations given to us. And that's it. Thank you.